While people are signing on, I just wanted to start by kind of giving folks a chance to let me know if they had more questions or just tell me how things are going. So I've made this Padlet page. You can also get to it on your day one. You should see something that looks like this, and you can add just little notes, any questions, totally anonymous unless you put your name in it, so don't worry about that. But if there's anything that you would like to share about how things are going, I'd love to see as we get people signed on. Yes, it's your choice. I'm not going to tell you not to. So there's one question about labs. So labs will all, to earn points for the planetary science badge, you just need to do the labs by September 17th. So there's no official due date for any of the labs, but they do take a while. They're designed to be done in kind of somewhere between an hour to an hour and a half. So putting all your labs off till September 16th would be a bad idea. So I've spaced them out. Another note that I will say on labs, I sent out an announcement last night, yesterday at some point, that has both the YouTube link for our video. Most of you were here, so I don't think you need to see that, but I also made just a little 7-minute video that goes through what each of the labs entails. So if you're wondering what the labs are, how you might want to choose some, that's a way to look at it and get a little overview. I also point out which ones have more math and which ones have less math. So if you want to pick ones that have less math, that's another way to find that out. And there is one lab that requires a measurement at noon. So that this goes through that and tells you that you'll need to, wherever you are, you'll need to make a measurement at noon to get one of the labs done. Okay. So today we're going to kind of cover two big topics. We're going to look at how astronomers map the sky, and then we're also going to talk a little bit about seasons, which might have been, if you looked at the reading, this was kind of the two things that were discussed in the readings. So we're going to start by doing a little activity. So this is the first activity in your day one. No, not day one, sorry. It's day two. My brain is already not working. Okay, so this is called Follow a Star. So this will take you to a survey. I'm gonna put you guys in some breakout rooms so you guys can do this together and talk with each other. I will be popping into the different breakout rooms to see how you're going, Can anyone tell me what were some of the challenges with describing the position of a star as you jumped between different times and locations?
I thought it was difficult because I was thinking if I was describing a star to somebody, I'd have to describe it either from directions or in reference to other stars. So if somebody knew they knew or they didn't know where my star was, they probably wouldn't know where other stars were either.
That's a good point. If you can describe the patterns though, that does maybe they won't know, yeah, where I think a lot of people chose stars in Ursa Major, so they were like UMA. They might not know where Alpha Ursa Major is or Beta Ursa Major, but if you can say it's kind of that thing that looks sort of like a dipper, then maybe that would be a way that we can use constellations to tie the stars to the sky instead of to a location. Anything else people found?
When I moved my marker to the North Pole, my star was originally kind of a little bit to the left of the north marker. When I switched to the North Pole, it ended up near the south marker.
Yeah, it's kind of amazing how much that changes things. There's also, this is something that the planetarium lab focuses on a lot, but the really nice thing about observing from the North Pole is that stars don't set. So the North Star will be directly overhead and all the other stars will just kind of rotate around it. So if you're in Walla Walla, most stars come up and then they go down. And like if you're at the equator, all stars kind of come up and go down. But at the North Pole, you could watch one star for an entire night. So they are moving a lot when you go to the North Pole. Cool. Did anyone, before we move on, anyone have any questions? Okay, well, if you do think of one and you want to put it in the chat, I've got that open. I'm going to keep going. So what you guys did when you were describing your star locations, is kind of similar to what astronomers do. So astronomers have a few ways of describing a star's location. The first one I wanted to run through is altitude and azimuth. So that's kind of what is shown here. It is tied to a location. So this would only work if everyone here was in Walla Walla and we were going out at night. I could tell you to look for a star using altitude and azimuth, but since we're kind of spread out across the globe, this way would never work. If I told someone in New York to look for a star using altitude and azimuth, they would find something different because this is degrees south of north is your azimuth, so north would be 0, and then you can go all the way around to 359 is your azimuth, and then altitude is degrees above the horizon. So you can go 0 is the horizon, and then 90 would be directly overhead. So this is a way that's really good, maybe if you're out with your family and you want to find a star while you're all together, but the second you do spread out, this no longer works because it is tied to your location like you guys just found. So all the other ways that we have of talking about star locations are going to be tied to the sky. Instead of your location, they'll be tied to the sky, kind of thinking, we call it the celestial sphere, where we're projecting out a sphere into the sky that we can then talk about no matter where you are, no matter what time it is, the stars will be in the same positions. So the first thing that we can do is we can add the north and south celestial pole, which is just, if you kind of, like this image shows, if you stuck a giant pole through the Earth and extended it out to space, it would be what is directly above the North Pole and what is directly above the South Pole. You can kind of do the same with the equator. If we kind of blow out the equator on Earth into space, you get your celestial equator, and we can look at, so if you were at the equator, the celestial equator would be directly above you. If you're at the North Pole, the celestial North Pole would be directly above you. Anywhere in between, those are kind of somewhere in your sky, but they are tied to the sky so they don't change with position. So this is kind of, we're starting to build a map on the sky instead of one that we just look outside. So this is kind of similar to thinking about latitude and longitude. Just like there's latitude and longitude lines on Earth, we can kind of project that into the sky. We have our poles and our equator, again, similar to latitude and longitude. Now we're just gonna also project all of the points in between onto the sky as well. So instead of latitude and longitude, astronomers call it right ascension and declination. And it looks a bit like this. So this is a little ugly, but essentially we've taken the latitude and longitude kind of coordinates and projected them onto the sky. Declination is going to be similar to latitude. So those are flat markers. 0 is at the equator, and then you go up to 90 at your north celestial pole, or down to -90 to get to the south celestial pole. Right ascension is then similar to longitude, sorry. And just like longitude, the 0 point is a little bit more kind of arbitrary. In longitude, we set 0 to be in Greenwich, England. So there's the Greenwich meridian is where we have set latitude or longitude equal to 0. That was decided because it was between Europe and North America, but it's really just arbitrary. You can set anything equal to 0. It doesn't matter. On the night sky, we set our right ascension equal to 0 at the position of the sun on March 21st. So that's how we define zero. It's just the position of the sun on the vernal equinox. So everything goes from there. We measure it in hours, minutes, and seconds. So you can kind of see it along this axis down here is our right ascension in hours, minutes, and seconds. Because these are tied to the sky, they don't change with location. It's true no matter where you are. And so if, the frontier fields are some deep space areas that Hubble looked at, so we'll talk about Hubble much later. We don't really need Hubble yet, but the Hubble Space Telescope looked at these 6 frontier fields, and I could describe any of these using RA and declination, and I could tell another astronomer, I'm from Wyoming, so I could tell my colleagues in Wyoming, I want you to look at RA approximately like 7.5, declination 40, and they could go out and look at the Hubble field 3 just like I was, even though if I told them it's altitude and azimuth, we would be looking at 2 completely different things. So RA and DEC are another way, kind of based on projecting Earth out into the sky. So this is the main way astronomers will talk about locations of objects. There are a few other things I want to discuss before we move on, but does anyone have any questions about RA and DEC yet? You want to put them in the chat as well? I've got that open. Okay. So just to look at this one more time, since I struggle with thinking about this 3-dimensional sphere kind of stuff. So this is just another model of that RA and DEC. I am moving on this video. The star I'm changing its declination. So when it's directly above the North Pole, it has a declination of 90. If it was directly above the equator, it would have a declination of 0. And so we can see it's not moving around the Earth at the moment. It's just moving, I'm just moving declination, so it's just moving up and down. When I change the RA, it moves around the Earth. But we can get a full 360 map of our nights, or full celestial sphere using these coordinates that I could, again, tell to collaborators either in Wyoming, or I also have some collaborators, I have some in Australia, I have some in England. We could all use this to work together to make sure we were looking at the same objects. So we won't really use these at all except for me mentioning it here. There's another kind of coordinate system that doesn't get used very often called the ecliptic, and that's just the path of the sun across the sky. So this is an RA and DEC map with the green line representing the path of the ecliptic. What this is useful for is if you're measuring the paths of the planets, they will all follow the ecliptic. So this is just the path of the sun, and the planets around the sky will be on this ecliptic. We can see, we'll talk about this more when we get to the seasons, but the highest point at the summer solstice, it goes up to an RA of 23.5 degrees, which is the tilt of the Earth. So we can kind of see how the sun moves in position in the sky depending on the time of year. And that is measured on the ecliptic. The other thing to note there, I do have a question about this, I think, in the homework, but because the planets are actually orbiting around the sun, they are not tied to the position in the sky. Like, they actually do move around the sky. Your textbook will talk about this as well, but the planets are called, the original word for planets comes from the Greek term wanderer, because the planets would wander around the sky, unlike the stars that were fixed in position. So, oh, I got a question. Can we go over what the frontier fields are? So those are, I actually didn't look this up. I will check and I will come back to that. It's not entirely important, but I think that'll be something when we get more into the galaxies and cosmology we might talk about more. We'll definitely talk about the deep fields, but I will look up what the frontier fields are for next class. Thanks, Bailey. Okay. So this is just, again, looking at that kind of celestial sphere. Sorry, jumping back and forth. Back to the ecliptic. The ecliptic will be 23 degrees from our celestial equator because it's the path of the planet and it's determined, path of the sun around the sky, path of the planets around the sky, and it's determined by that tilt of the Earth. So don't worry too much about this. I don't like thinking in 3 dimensions. It hurts my brain for some reason. So I kind of blow past this. The main thing to remember is how astronomers use RA and DEC to describe positions, since altitude and azimuth are tied to location. Okay, and the last thing I wanted to go over just quickly is that there's also, with the RA and DEC, astronomers have broken up the sky into 88 constellations. So what you can see here, this map kind of has everything. We've got our lines of RA and DEC graphed out. They're a little hard to see. They're the darker lines in this image. And then the orange lines represent the area for each of the 88 constellations. So astronomers can also say, I'm looking at a star that's in Boötes. So this is Boötes right here. And maybe if it's the brightest star in Boötes, it'll be Alpha Boötes. And I can go look for the brightest star in Boötes. I'll know that area of the sky based on that. We've got Draco, Ursa Minor, looks kind of stretched out because we're stretching out we're taking a sphere and we're stretching it out. But you can kind of see that's Polaris right there. So that's the pole star right at 90 degrees in declination. The other things that are marked here, again, we have our ecliptic. So that's the path of the sun, where it is at different times of the year. And then they also added in the Milky Way, the plane of the Milky Way galaxy. So if you look out, if you're somewhere dark and you look out and you see fuzziness, that's your Milky Way. So we could also use that as a reference point because that'll be tied to the sky and not to your location. So yeah, I think that's all I wanted to say there. Again, any questions? Okay. Once you know the position of the stars and you can compare them to, so we know what, sorry, let me back up. We know that when we went to the North Pole, we saw the stars move. So we can use that motion as we move around the Earth to actually figure out where you are. So this is celestial navigation, and it's been used since early days. We can use the position of the stars in the skies to determine where we are on Earth. So if you measure the angle of an object above the horizon, you can use that to determine mostly your latitude. Longitudes were usually determined using the position of the sun at very specific times. And it's actually one of the reasons clocks were invented, was so people could go on long sailing trips and they would know where they were based on the time of day and where the sun was in the sky at that time. I will point out, I am going to send this out right after class, I think-ish. There's a great podcast. It's one of the best podcasts I've ever listened to talking about celestial navigation. So if you're interested in doing a podcast project, you'll get that one coming out. I like almost cried the first time I listened to it. It was just so beautiful. So highly recommend that. Yeah, I think this is, again, just kind of showing another way of representing that celestial pole and ecliptic. The next slide is more fun, so I'm going to start forward. So the other place, I won't have a Disney clip every day, I promise. But because in Moana, Moana uses celestial navigation, I like to show part of this. At night we name every star, we know where we are, we know who we are, Oh. Sorry, I didn't play the whole song. But what you'll notice is that they were using something, they were using their hands like this. If you spread out, pretty much everyone, if you extend your arm and you look from your thumb to your pinky, that is about 15 degrees on the sky. So they were looking, measuring the size where Orion was. You can kind of see in the movie. At night we name every star, we know where we are, we know who we are, That's Orion. So they're measuring this angle of Orion to the horizon using their fingers, knowing that this is this, and they can find where they are based on how high above the horizon different stars are. So Moana does actually a fairly good job of representing some of the ways indigenous communities, specifically in the Pacific, use the night sky and very good maps of the night sky to travel out into just kind of to map the directions to different islands around the Pacific. So the other thing, I do want to pop back here, sorry. Yeah, so because we are in the northern hemisphere, the thing that we have really nice for celestial navigation is that we know the North Pole, we know Polaris, the North Star, should be at a declination of 90. And depending on its altitude above the horizon, sorry, had a little brain fart there, we can tell where we are in latitude. So your latitude is actually equal to Polaris's distance from the horizon. So if you were at the equator, Polaris would be right at the horizon. If you're at the North Pole, Polaris will be directly above you at zenith at 90 degrees. So anywhere in between at Walla Walla, we're pretty close to 46 degrees in latitude. So Polaris is about 46 degrees above the horizon. So you can use that no matter where you are to find your location on Earth. Or not no matter where you are, because once you go below the equator, you have to use the southern pole and there's not a star there, but there's some nearby. So based on that, I'm gonna start a poll. I've given you 3 images of the night sky in 3 locations. All are on similar scales, and I've circled Polaris in each one. Which one is the furthest north? So yeah, it's a little hard to see, but we got a green dot for Polaris, and a green dot for Polaris. We got 12 answers. I think there are 27 of you. Ooh, that was a bunch right there. 16, 17, 20. Oh no, there's 26 of you, because I am also here. I am not voting. My brain works. I think 5 more people. Okay, so we've got a pretty good split at the moment. About 52% of folks are saying C and 52 are saying B. Could someone who said B explain your reasoning? Or C? Now you should be able to see where everyone fell out.
I just kind of took a guess because it's circling the north indicator. Like it says northwest, north, northeast, and it's just circling the end, so.
So that circle is actually Polaris. It's a little hard to see. So that is actually a bad sign that it's circling north, because that means it's right at the horizon. So sorry, this was a little unclear, but again, we want our Polaris star to be as far from the horizon as possible if we are going further north. So actually C is going to be the right answer for this question because it's highest in the sky. So that's kind of the idea. Higher Polaris is in the sky. I think I didn't describe the question well as well, but the further north we are. So this will be kind of similar to what we do in the planetarium lab.